People will be aware of the RAS fellowships, and we have an RAS Postdoctoral Fellow to talk to us today, Dr. David Marsh from King's College London, talking about studies on Axion dark matter. David.
Thank you very much. So, okay, thanks. Present to view. Okay, so I'm going to tell you about Axion dark matter. Hopefully I'll explain what that is. And I'm going to frame it as a kind of story of what happened for me during my time as a RAS postdoctoral fellow, because as of a couple of months ago, I've now moved to Göttingen, and I was also asked to kind of tell you about what's going on there and how I've got there from being at the RAS. So, the effects of dark matter are, as you all know, observed on many astrophysical scales, all the way from dwarf galaxies up to cosmological scales. And this, I'm a cosmologist, I'm a CMB cosmologist mostly. This is my favourite evidence for dark matter. This is the Planck all-sky lensing map. So this is the integrated effect of dark matter along the line of sight from the CMB, reconstructed from 4-point statistics. And it effectively gives you an integrated map of dark matter on the sky. So, these are like larger than degree scale coherence in the dark matter. And it shows you what's very important is that the dark matter was present at very early times, and it was the seeds for structure formation. This gives you this whole picture of the linear CMB growing into nonlinear structure and dark matter being there. And dark matter is about 85% of the total matter content of the universe. What do we really know about dark matter? So we often say, we know that dark matter is cold dark matter. There was a question earlier about warm dark matter. So what do we actually know? What does that mean? So we know that dark matter is cold if it's thermal. It doesn't have to be thermally produced. And that means that it's non-relativistic when it was produced. And that's something that we know from the CMB and from galaxy surveys like the Southern Digital Sky Survey. We know that the dark matter is collisionless and has no interactions beyond gravity. So this is, famously illustrated by the bullet cluster. Here's that famous picture of where lensing was used to map the matter distribution. X-rays were used to map the gas, and the matter distribution is displaced from the gas, so the dark matter goes right through it. So it's collisionless on the scales on which we observe it. We know from the CMB, from knowing that those structures, those seeds for structure formation were there from the CMB and from the baryon acoustic oscillations, but dark matter had to actually have been produced sometime, quite a long time before the CMB. It was present in the universe, very early on, being redshift of something like 10 to the 5 at least, up to 10 to the 7, say. We know also that it forms bound structures, that it forms halos, but we only have obviously a lower bound on the smallest bound structures. My favourite bound is from the disruption of tidal streams, very interesting work by Bovey and Erkal and their collaborators. So by looking at the disruption of tidal streams, so the PAL5 stream has these holes in it, and it is inferred that these holes are caused by the passage of substructure in the Milky Way of around 10 to the 6 solar masses through tidal streams. We know that, on the other hand, the dark matter is not predominantly made up, Bernard in the back there, Bernard's going to disagree with me, is not predominantly made up of bound small compact objects like machos and primordial black holes, or at least there are very strong constraints on these models across a wide range of their parameters. So if they're subdominant components of the dark matter across a lot of the range. We know this from observations like microlensing. I'll talk a little bit later about the Subaru hyper-suprime cam microlensing, but also historically EROS. We also know, and this is partly my own work, that the dark matter is approximately one component, that it's a single degree of freedom, plus the small contribution of massive neutrinos. But the important thing about all of these statements is that everything we know about dark matter comes from gravitational interactions, and that all of these statements are scale dependent. They all apply on a particular scale, and some of them we know have to break down in particular theories of dark matter. For example, for a WIMP, the dark matter can't be completely collisionless. It has to have an annihilation cross-section, for example. It also can't be completely cold. There is a scale at which thermal free streaming does happen. So all the models have to break down somewhere, and all the observations are scale dependent. So I'm interested in how we can push all of those things that we know about dark matter. So I'm going to tell you about axions and axion-like particles. So where did they get their name? They are actually named after the cleaning product. They were named by Frank Wilczek. Frank Wilczek is my academic grandfather. He has a Nobel Prize. Nothing to do with axions, though. It was to do with the asymptotic freedom of quantum chromodynamics. And he decided to call these particles axions because they cleaned up a mess in theoretical physics. And he thought it was a nice name, and it is. So what mess do they clean up? So as well as being an astronomer, I was trained as a particle physicist, a theoretical physicist. So I'm going to do a little bit of a detour into theoretical physics for you. So as a theorist, I think of everything as a Lagrangian density. And Lagrangians are numbers times operators. So operators tell you what physical effect you are looking at. So this operator might be something like, an electron coupling to the photon 4 vector. So you had E bar, gamma mu, A, E, and that would tell you that electrons scatter off electromagnetism. In this case, the operator that we're interested in happens to be the operator that gives rise to an electric dipole moment for the neutron. And then the numbers are the things that you measure. So it tells you how strong this effect is. But the numbers aren't just numbers. Often they come from different parts of physics. So it's a sum over physics of different contributions. In the case of the neutron electric dipole moment, there are contributions from the strong nuclear force and from the weak nuclear force. From the strong nuclear force, it's from topological configurations of the gluon field. And from the weak nuclear force, the contribution comes from CP violation from the Cabibbo matrix. Okay, so the neutron electric dipole moment is, people try and measure it in the lab. I'll tell you about some of those experiments later. But it's measured consistent with 0. There's an upper limit. And this implies a delicate cancellation. It implies that these two different contributions to this number add up and cancel at the level of 10 to the minus 10. And particle physicists don't like coincidences. We say these things are unnatural. So you need to clean up this mess. This is where the axion comes in. So if you remember, a favorite tool of particle physicists is spontaneous symmetry breaking. So spontaneous symmetry breaking, you have this wine bottle potential, and it has a rotational symmetry, but the ground state is here, and the ground state, you have to pick a particular field configuration, spontaneously breaks the symmetry. Just like if you're sat all around the circular table having dinner, and there's equally spaced water glasses out for everybody, so that it's completely rotationally symmetric. But when you sit down, you have to take one of those glasses. So you have to break that left-right symmetry. Someone has to choose which glass to take. That's a spontaneous symmetry breaking. And this is spontaneous symmetry breaking. And so you have the wine bottle potential and the analogy of taking your wine glass to break the symmetry. Okay. You're getting analogies on the feet here. Okay, so this angular direction here we call Goldstone bosons. So this is a massless so this excitation now around here corresponds to a massless particle. Thanks to Nernst's theorem. So this particle, this theta, this angular degree of freedom in the complex plane, has a continuous what's called shift symmetry. The physics doesn't care where you are around here, and that just reflects the underlying rotational invariance of the potential. So the trick here is to couple this Goldstone boson to the problematic operator in your Lagrangian. So what that means is you turn this, what was a number, into a number plus theta. Then, because of this shift symmetry, I can just make a field redefinition of theta and absorb the number into theta. So now, instead of having a number, I have a field. Okay, obviously this only works for a certain type of operators, where your number is related to a compact variable. This happens to be the case for the neutron electric dipole moment. Then we tilt the wine bottle. So what does this is some object called an instanton, some quantum mechanical effect. But this tilts the wine bottle. And now, although you've got this field theta, it's now got a preferred location. And thanks to symmetry, this preferred location is 0. It's a symmetry. This restores a symmetry of the action, so it's preferred. It restores charge parity invariance. And so now the field evolves dynamically. You picked some value that was the same. You absorbed this problematic number. You tilted your wine bottle, and now the field evolves, and it goes down to the bottom, and it oscillates about this preferred bottom. A bonus of this is that the oscillations in this field theta carry energy density. Okay? So the oscillations in the gradients, the spatial gradients, the temporal gradients in this field carry energy density. And these field variations behave like dark matter. So that's what Axion dark matter is. It's a very weird type of dark matter if you think about it this way. It's not some collection of cold billiard ball-like particles, like a WIMP. It's really, the dark matter is spatial and temporal, energy stored in spatial and temporal variations of the neutron electric dipole moment. That's quite odd, but that's what it is. Of course, there is a particle associated to this field, that's why it's called an axion. But and this type of dark matter is some 10 to the 15 times lighter than a standard WIMP called dark matter. So you're going to look for it in very different ways. It's not these tanks of water, tanks of liquid xenon in a mine and scattering like this. It's things like spatial and temporal variations of the neutron electric dipole moment. Okay, so that's the QCD axion. I'm also interested, there are other types of axions. And we come to thinking about these by thinking about Kaluza-Klein theory and string theory. So in general relativity, we're all well aware that we use fields to describe the geometry of space. So in cosmology, when we have the scale factor is a field. And the scale factor describes the size, the geometry of space. In the last talk, we had some discussion of topology, so here's some more. So a torus requires two fields to describe its geometry. It has two moduli that describe the shape. And in general, any surface with a given topology requires a certain number of fields to describe it. So the number of fields that you need in general relativity to describe the geometry of a surface is specified by its topology. So in a theory like string theory, as well as having these numbers that we need to describe the surface, thanks to supersymmetry, these topological moduli are paired up with a different type of field that has the characteristics of an axion. String theory, as you're probably well aware, naturally lives in 10 dimensions. And so you have to wrap up those 10 dimensions so that we don't see them. And the ways that you can wrap up 10 dimensions can be topologically much more complex than things like a torus. And this is just a cartoon to illustrate that degree of complexity of 6-dimensional manifolds. This is a famous projection into 3 dimensions of the types of manifolds we think string theory lives on, what are called Calabi-Yau manifolds. And just like we had the Euler characteristic to describe the connectedness of surfaces in 2 dimensions, the geometry of these surfaces, all the topological invariants, can be constructed from 2 numbers called the Hodge numbers, H11 and H12. And a lot is known about these types of manifolds. So this is a projection of 400 million known different manifolds of this type. And here are its Hodge numbers. And so the number of axions is given by some particular sum of the Hodge numbers called the Betti numbers. And this is the statistical distribution of the known manifolds. And it has a lot of symmetry and a lot of structure, but it has this large peak. So most manifolds that we know, almost all manifolds that we know, have about 30 axions living on them. Okay, so But why do we care? So the characteristics of string theory, you know, extra dimensions and supersymmetry. But we don't have to be able to see these things in our universe. They can hide way up at the Planck scale. You don't have to be able to see extra dimensions or supersymmetry in the Large Hadron Collider for string theory to be right. They can hide. They can be at very high energies. But the existence of these many different axions, you know, up to 30 different axion fields, appears to be a generic low-energy prediction of string theory. So the axions are very light. They're low-energy degrees of freedom. And the existence of many of them appears to be a generic prediction of string theory. So the range of products available from the Axion company, they must love all this free advertising they get from particle physicists, is much larger. So axions, so there might be some axions that have the right characteristics to be dark energies. There might be some axions in that spectrum of 30 that have the right characteristics to contribute to dark energy. There might be some axions that have the right characteristics to contribute to inflation. And in fact, axions can even play a role in baryogenesis thanks to their role in charge and parity violation with operators like the neutron electric dipole moment. So they're very interesting for cosmologists because you think there are many of them. But the catch is, string theory doesn't make a definite prediction. It says they should be there, but all it tells you is that the masses and couplings of the axions are specified by the moduli. But we don't know what values these moduli fields have, how big the extra dimensions are, essentially. But we can treat them as probability distribution functions. We know something about the probabilities, so we get statistical predictions about what should be in the universe. So based on these observations, I wrote my application to be an RAS Postdoctoral Fellow. And the name of the project was Precision Cosmology of Axions and Moduli. So I've got a couple of passages from that here. Axions and moduli are model-independent predictions of string theory that could explain dark matter, dark energy, and inflation. When axions are dark matter, their small mass imprints a scale on galaxy formation. I will develop theoretical techniques to look through the effects of axions using planned ground and space-based telescopes. The string landscape can be understood in terms of distributions of random matrices and functions. I will study these statistics to elucidate the phenomenology of moduli and axions and use cosmological observation to locate our universe within the landscape. My research will constrain the properties of axions and moduli via their gravitational effects on cosmology, answering two key questions. How does axion dark matter affect galaxy formation? And can the string landscape make predictions about cosmology? So to cut that down, I'm not going to talk about inflation, and I didn't. I don't actually think inflation is very interesting. I don't think we can learn very much about it from observations. It's a bit of a thorny issue. I also don't think we can really locate our universe within the string landscape. That was a bit overambitious. If I want you to take away two things about the physics of axions and moduli from this talk, they are these. The very small mass of axions, I said 10 to the 15 times at least lighter than a standard WIMP, imprints a scale on galaxy formation. So the axion mass is related to a scale in cosmology. It's a cosmological scale. To give an example, if you take my favorite axion mass, 10 to the minus 22 electron volts, you take the virial velocity in the Milky Way, this is why it's my favorite mass. You take the virial velocity in the Milky Way, you make the de Broglie wavelength 1 over mv for that. The length scale is 1 kiloparsec. That's an interesting cosmological length scale. So you can make axions have effects on galaxies because of the de Broglie wavelength, essentially. Okay? The other thing I want you to take away is that we can describe this kind of thorny issue of string theory, and we can get some relatively general results from random matrix theory. So just like we have the central limit theorem for statistics of numbers, we have random matrices in string theory, and there are a lot of powerful results from random matrix theory that make predictions about these distributions for axion masses and couplings. Okay, and I'm going to focus on how does axion dark matter affect galaxy formation. So, my 2 years as an RAS fellow, these are all the papers that I wrote on this topic. So, without looking much further at it, I think you can say that this was an incredibly productive time for me. There's about 16 papers written, mostly in small collaborations. The freedom that I was given on this topic as an RAS fellow was excellent. I worked a lot with my hosts at King's College. A lot of the papers were collaborations I started when I got there. And I highly recommend these fellowships. I had a fantastic time and produced a lot of work. I'm going to spend the last 5 minutes or so of my talk giving you one slide each on a small selection of those papers to try and give you a feel for what we actually did, what I and my colleagues did during that time. The first one is, I said at the beginning, I'm a CMB cosmologist. You might not believe me anymore after spending so long talking about particle physics, but I am a CMB cosmologist. So here, I said the CMB can constrain whether dark matter is single component, and this is an example of that. So here, we wrote a CMB code, a Boltzmann code, that includes the effect of cold dark matter plus an axion. And I said that our statements about dark matter are scale dependent. So if I make the axion light enough, this is the mass in log of the mass in electron volts. So the proton's 10 to the 9 electron volts. This is a lot lighter than the proton. But if the dark matter contains a small fraction of very, very light axions, then the CMB can put constraints on that fraction. This is the fraction. And here, I'm just showing you the allowed fraction in different mass bins. And the color scale here is proportional to the probability in that bin. The variance in the bin is just a visual artifact of the way I've represented the data. So here, we used data from Planck. For adiabatic initial conditions, we used the temperature, polarization, and lensing. I showed the lensing map earlier. And we're able to tell you that basically the dominant component of dark matter has to be heavier than 10 to the minus 24 electron volts. You might think that's a very, very small number, but this is the lower bound on dark matter particle mass from well-understood linear observables. I don't know of any model where you can make the dark matter lighter than this. So that's why it's an interesting thing. It's the lower limits, it's the boundary of what we know about dark matter. If it's a particle, it has to be lighter than 10 to the minus 20, has to be heavier than 10 to the minus 24 electron volts. If it's lighter than that, its contribution, the square root omega AH squared for visual purposes, its contribution has to be less than a few percent to the total dark matter abundance. This is what we mean by single component. This is what we mean by, cold, predominantly cold and collisionless. That it blows up again at 10 to the minus 33 electron volts. That's because that's the inverse Hubble scale measured in particle physics units. Lighter than this, I said axions can be dark energy. Lighter than this, you're contributing to dark energy. Okay. The next slide I'm going to show you is effects of axions on galaxy formation. So here, this is the money plot from a paper I wrote with Alma Gonzalez Morales, Jorge Peña-Rubia, and Luis Serenia Lopez. So here, the scale now that axions imprint on galaxy formation, this kiloparsec scale for a mass of 10 to the minus 22 electron volts, leads to the formation of bound objects that we call axion stars. And these objects should form in the centers of galaxies and lead to flattened density profiles compared to cold dark matter. And so here, what we did is we did two things. We wanted to try and say, can we get a bound on the mass from the density profiles of the classical dwarves? So we started off by showing that you can't do this with genes analysis. So we did a genes analysis of the 8 classical dwarves, and we found the preferred mass related to what's called the cusp core problem. But we're better than that. We also did n-body simulations, and we tried to work out whether this was a biased or whether the genes analysis was biased or unbiased. And it turns out that due to the anisotropy degeneracy in the genes equations, genes analysis is biased, and you cannot use it to infer the mass of the axion from density profiles. We found that there was another unbiased estimator, and when we applied it, if the axions are solving the cusp core problem in Fornax and Sculptor, so we used the 2 components. So in Fornax and Sculptor, you have 2 different components of stars that you can separate based on their metallicity, and then you can use an empirically derived relationship between the mass and the half-light radius of the stars to infer the slope of the density profile. when we did this, we found that you had to have if you want to explain cause with a particle, not with, say, supernova feedback, you have an upper limit on the particle mass of something slightly smaller than 10 to the minus 22 electron volts. Unfortunately, cosmology, the formation of high redshift galaxies, wants you to be a bit heavier than this. So there is a tension between using ultralight axions to explain the cause in dwarf galaxies and having successful cosmological structure formation, such that you probably can't really consistently solve the cusp core problem with an ultralight axion. But there are caveats to this as well. 1 minute left. I have 3 things I can tell you about, so I'll tell you about one of them. I will tell you, okay, random matrix theory. No, let's not talk about that. Let's talk about the spatial and temporal variation of the neutron electric dipole moment. This seems like the most obvious signature of this model, right? I said axions are an oscillation in the neutron electric dipole moment. Has anybody looked for this before? The surprising answer was no. So we, Malcolm Fairbairn, my colleague at King's College, we called up an old friend of Malcolm's who works on the neutron electric dipole moment experiment based at the Paul Scherrer Institute near Zurich in Switzerland. And they've taken data on the neutron electric dipole moment there and at the previous incarnation of the experiment at the Institut Louvre-Langevin. So they have a neutron source and they get some ultra-cold neutrons and they put them in a bottle and they do something called Ramsey interferometry. They push them into the bottle, they allow them to spin, process in a magnetic field and an electric field, and then push them out. And by measuring the neutrons that come out with different spins in different directions, they can infer whether the neutron has an electric dipole moment or not. And they've done these experiments for years, and they basically and in the old version, they basically logged the value of the neutron EDM every day. And in the new version, you can get a measure of it about every 130 seconds. Turned out they never looked at this as a time series and looked for time variations. They just prevent the integrated, value as if it were static. And we said, let's do a time series analysis of this. And they were very nice. They said, yes, this is a great idea. Here's 2 graduate students to do the analysis. Absolutely fantastic. Very, very talented graduate student, Mikhail Rolik at the Paul Scherrer Institute, did this analysis. And we were able to rule out a region of axion parameter space that beats, so if the axion couples to the neutron EDM, this is the strength of the coupling. This is the QCD axion, it's a line. If you couple to the neutron EDM and you have a given mass, we rule out all this part of parameter space. Much stronger than the constraints from supernova energy loss. Stronger in a region that's interesting for galaxy formation than the constraints from Big Bang nucleosynthesis from the abundance of light elements. But not strong enough to rule out the QCD axiom. This is very interesting because there's a new series of experiments that are under construction in Mainz in Germany and in Boston in the United States called CASPER. And their first projection is to get down here. And in the final incarnation, CASPER intends to eat into some of this range of parameter space given by the QCD axion. Our results are a very important first laboratory constraint on this type of interaction to provide a baseline for these proposed experiments. Okay, so that is the end of my talk. And I will just tell you, I was asked at the end to say, life after London, I've left. When a person is tired of London, they are tired of life. So why would I go to Göttingen? Right? The reason is that the Humboldt Foundation, I won a grant from the Humboldt Foundation called the Sofia Kovalevskaya Award. This is Sofia Kovalevskaya. She was the first female professor in Europe, I believe. And the award is named in her honor. And it's kind of like an ERC starting grant without all the administrative strings attached to it. So it's for 1.65 million euros over 5 years. So that's me, 2 postdocs, 2 PhD students. I think you'll agree that's a reason enough to have to leave London, much as I would prefer to stay. I would just like to say that this is a fantastic opportunity, and I wouldn't be here if I hadn't had my very productive 2 years with the RAS funding first. So thank you very much to the RAS for that opportunity, and thank you for listening.
for one question, and Claudia's got a hand up already.
I have a question, but the first is a comment. Because the first female professor was in Italy in 1600 something at the University of Bologna. I need to correct that.
Okay.
Lovely. But the talk was fantastic. I wonder why for the Casper core problem, you could not use massive galaxies, which have much more signal in the center, where this problem is very severe, actually, because these dwarf galaxies, they are very faint. I understand.
Right, so,
yeah.
so the reason we looked at it, so you mentioned that there are cores in other types of galaxies, in LSBs perhaps, and also cores in clusters. The reason is that you definitely couldn't explain those cores with an axion. Those cores are much bigger, and it turns out that this coherence phenomenon for axions, the core size, so the cores are given by ground states of the equations, so they're a one parameter family, and the core size, as you increase the core mass, gets smaller. So it's like it's like you're trying to form black holes, right? As you increase the mass, the things get more and more compact. Eventually, they collapse into black holes, and the cores in clusters and LSBs are very massive, but also very large. And if you wanted to get such cores from an axion, it would be in strong violation of the cosmological constraints. So the reason we wanted to try and explain the cores in dwarf galaxies is because you can just about live on this knife edge where you can explain the cores and be consistent with cosmology. You can explain the cores without recourse to baryonic feedback. So that was why we went. So that was why we looked there, because it's the place where we could try and live on a knife edge and make maybe a prediction for a new observation.
Okay, I think we have to thank our speaker again.